Okay, good afternoon. I think we can start. We'll not expect the 15 minutes of academic freedom to come late. So my name is Lucian Hoffmann. I'm the director of the Environmental Research and Innovation Department, and so I'm happy to welcome you for the second lecture in the series on enabling technologies for the clean energy transition. And energy, as you know better than me, is a worldwide challenge. There will be an ever-growing demand simply because the population will increase. There will be also more and more penetration of renewables, which puts a lot of stress, of course, on the whole system and how to organize the system. We'll also move more and more to more energy storage that we will need to handle and manage the whole system, electric vehicles and prosumers penetration. So there will be also no new business models coming from the central production to the end user. Now each end user at the end becomes also very often a producer. The distributed grids and controls, as I said, often we have a central production, and we will go more and more into a distributed production of the energy. And still today, there's around 1 billion people without any access to electricity. So the universal access to electricity is also an important challenge for the future. And to do this, to handle all these challenges, we need, of course, to evolve and go to a next generation energy system management, which will be more and more intelligent. So we need to introduce new technologies like artificial intelligence, new communication capabilities that will be able to also meet the last mile for many devices. So to go to smartphones, to have smart bulbs, smart plugs, and so on. The digitalization will be more and more important. So Internet of Things will enable a massive processing of bits coming from smart devices connected all around the globe. Also a very important objectives that we have worldwide, and especially also in Europe, is the decarbonization of our systems, and of course also of the energy systems, and so to go more into renewable energy systems. As already said, going from a centralized to a decentralized organization of energy production, which will be closer to the energy consumption, relying on distributed energy resources for generation, but also storage and demand. Traditional energy systems that will evolve into a multitude of systems, and so we need to organize these systems, of course, that at the end globally this still works, and there will be new business models as energy becomes an asset also for the consumers and not only for the producers, and so we need to have also new platforms for secure and fair trading. At least, so we have now set up since a couple of years a new unit on energy systems, clean energy systems, with a number of products and services that we develop, and we focus on 6 domains: battery storage, to introduce these technologies and solutions for the operation and control of the energy systems, energy communities, develop new tools and digital solutions for the management and operation of local energy communities. Electric vehicles, which are becoming a very important part of the equation, and if all vehicles would be electrical today, we could not handle this from the energy systems point of view, and so we need also there to develop new technologies and tools to introduce or to host more electric vehicles than today, and also, say, not only using charging stations to give electricity to the cars, but also vice versa, using the energy that is stored in the batteries of the cars to maybe feed the energy system. active buildings, so develop smart tools and algorithms for the energy management and to have more energy efficient buildings, which is of course an important part also of the equation, is to reduce the energy demand, digital twins, and finally power electronics. And for this we have established a real-time hardware-in-the-loop laboratory that helps us to model things, concepts that we develop to test them in an still laboratory environment. But then, of course, as a research and technology organization, we want to bring technologies to the market. At the end, we also want to test new technologies, new solutions in real conditions. And there we are presently setting up an energy living lab with a focus on battery systems that to integrate them in the energy management of local communities. And well, to foster this and also bring insights from abroad to Luxembourg, to Luxembourgish stakeholders. So we thought that it may be of interest to organize a lecture series. And I said this is the second lecture in this series. You see, we'll not go into the detail that this will go until May next year with more than 10 lectures of internationally recognized specialists. And each time we try to bring them in contact with the local community. And I want to thank Professor Pedro Rodriguez, who put this all together, and also the National Research Fund, which supports this lecture series financially. And today, so we have the pleasure to have a lecture by Professor Nallanathan from University of London. Some important steps in his career. So in 2000, he received his PhD at the University of Hong Kong. Then he moved to Singapore, where he became assistant professor in the Department of Electrical and Computer Engineering. Then he moved to Europe, where he still is in the UK, first at the King's College, where until 2017 he was professor of wireless communications. And since 2017, he's at the Queen Mary University of London, professor for wireless communications, and also the founding head of the Communication System Research Group in the School of Electronic Engineering and Computer Science. And so he will give us very important insights on artificial intelligence for massive Internet of Things in clean distributed energy systems, which is one of the technology that will help us to manage the whole system. But before giving him the floor, I just want already to announce the next conference, which will take place on the 23rd of October by Professor Julio Romero Agüero from Quanta Technology from the US, who will talk to us about grid modernization towards smart systems for the clean energy system. So please write down already in your agenda this next session. And with this, I give the floor to Professor Nallanathan for his talk, and Baya will help us to bring this on the screen.
Technology, right.
Thank you.
They don't want to show your presentation. They say no, they don't want to put your presentation. I have just to. Silva, is this one? I don't know why they. Yeah.
You put the first slide.
Oh, this. Hold on. Hold on. on the screen actually.
Yeah.
It's this one. It's this one. But the view didn't want to go on the slideshow.
Okay, I can do it.
Maybe I should,
Yeah. Now I can do it.
but they will not see your
No, I
slides.
can do.
It's okay.
I can do it. Yeah. Yeah.
Be careful because you have people online.
There's mouse here. Ah, here. Okay. There's a mouse here.
It's on the screen.
Bring it to here. Okay, play it
see?
here.
No.
Wait.
Okay. Oh. Hold on.
Yeah. Okay, I can do it here.
Yeah, you can. I think that's
Okay.
I think you could go on. Yeah.
No.
Check if the people online could see. You could go.
Okay, fine. Okay, good afternoon. Thanks, Lucian, for the kind introduction. Thanks, Petro, for organizing this talk. So actually, my background is in telecommunication engineering, not energy systems or renewable energy. How many of you with the background of telecommunication engineering? Only one. Okay, only two. So actually, I will try to explain the concept without any equations or anything, such that any person with average knowledge could understand. So here, if you take the 5G, not like 3G, 4G. So here we have, in addition to broadband, we have Internet of Things. So if you take the use cases, so here we are going to have two types of IoT we have. One is the massive IoT, other one is the critical IoT. So the 5G sits on these three types of use cases. If you see the difference between this, the massive IoT, the left-hand side bottom corner, and the right-hand side bottom corner, the differences are significant. For example, if you take the massive IoT, so you are going to have smart metering comes under the massive IoT. So if you take the smart grid, automation comes under the critical IoT. So if you see the requirement of, you can take this one. If you take the requirements of massive IoT, here the low cost, low energy, small volume of data. But if you take the critical IoT, so here you need reliability and very low latency. But here, if you take the smart metering, so you don't need the latency is not an issue. So that means if you cannot send the smart meter reading now, you can send it after 1 hour. So latency is not an issue. But here you have huge number of devices. If you take a city, you are going to have millions of smart meters, but small packet of data. So here the thing is, say, in smart grid automation or other applications. So here we need high reliability, 99.9% reliability we need. So at the same time, here we need very low latency. Low latency means in 1 millisecond or 5 millisecond, very low latency we need. If you take the 6G, so now 5G, so implemented in most countries. Now if you take the 6G, so here we are going to have, in addition to this massive IoT and critical IoT, we have sensing application. So here, so the sensing is, so it is going to be the driverless car, autonomous vehicle. So we need the sensing, localization and mapping is very important. Or auto-guided vehicle or automatic mobile robots. So you need sensing, localization and mapping. So now if you take compared to 5G, in 6G, all these 4 use cases sits on artificial intelligence. So artificial intelligence are going to be used in enhanced mobile broadband, on massive IoT, critical IoT, so in sensing. So now here if you take compared to the 5G in 6G, so everything is going to be a factor of 10. So compared to 4G and 5G, a factor of 10. Now 5G to 6G, everything is going to be a factor of 10. So these are the topics in communications to improve the performance. So now I am not going to consider that. Now we are going to see, so in the 6G, there's going to be a new use case that is going to be the combination of massive IoT and critical IoT. So that means, so we are going to have, earlier we had the massive IoT and critical IoT separate. Here, this requirement and these requirements are separate. So here the requirements are totally different. But in 6G, we are going to have some new cases where we need both combination of the massive connectivity, at the same time reliability and latency, very low latency, 99.99% reliability, at the same time massive connectivity. So this is going to be a very challenging task, because even in 5G, so here this problem, this critical IoT problem is still not resolved here. So this problem is still not resolved in 5G. So how we can achieve 1 millisecond latency with 99.99 reliability is still not resolved. So then when we have in 6G, the standardization body considered a new use case, the applications of massive ultra reliable low latency communication. So if you take the requirements according to the standard requirements, so in smart grid, so we are going to have the latency. If you take the electricity distribution for medium voltage, so 25 milliseconds. So if you take high voltage, the latency is 5 milliseconds. So some other applications, so here we have some other applications. We have 0.5 millisecond here, automation also 1 millisecond, but in smart grid, so we have 5 millisecond and 25 millisecond. So therefore, this critical IoT or ultra reliable low latency communication is going to have the 2 important use cases. One is smart grid, other one is industrial automation. So now the question is, so in all cases, we need the reliability of 99.9% reliability needed. So this is the specification in the standard. So now the question is how we are going to achieve this latency, how we are going to achieve this latency, and how we are going to achieve the reliability. That is the challenge here. So now if you take the IMT 2030 vision, so here compared to the 5G, so here we are going to have sensing with communication. At the same time, we are going to have artificial intelligence is going to be integrated with the communication. So So because if you have the artificial intelligence only, we can optimize the dynamically, we can optimize the system. So we need, so the system should be changed every millisecond. So now if you take the vision of IMT 2030 is to achieve the energy efficiency. So that means to reduce the greenhouse gas emission. So that is the vision of IMT 2030. So now even in the communications or in other every area, so the main thing is how to address the problem of climate change. So energy consumption reduction even in communication area. So now if you take the ICT sector, now the mobile communications consumes 0.5% of the global energy supply and contribute for 2% of CO2 emission. So the ICT technology. But by 2030, it is going to increase by 100 times by 2030. So therefore, since it increases exponentially, so ICT sector is going to contribute for the global CO2 emission significantly. So that's what IMT 2030's vision is, how to reduce the energy consumption. So here, if you take in the next 10 years, if you take the ICT sector, so energy consumption is going to increase here next at least 5 years. The main reason is, so if you take the emerging applications, metaverse or digital twin or autonomous vehicles, so when we have more and more functions needed, when we add more functions, so actually they are going to consume more energy. So for next 5 years, for short term, so because of the explosion of data and emerging applications, so the energy consumption of ICT sector is going to increase. But in midterm, so maybe in after 5 years for midterm, so the energy consumption will fall because the wireless networks become the green, and at the same time, so it is the most likely the smart grid and the cellular network base stations are going to be integrated. So such that, say, if you take now in the communication sector, 70 to 80% energy consumption from the base station. So now the base stations are going to be integrated with smart grid with the renewable energy sources. By that way, so we can reduce the energy consumption. Then, so for long term, to reduce the energy further, so we have new communication scheme that is called semantic communications. So that means, so we don't need to transmit all the information. Say, for example, in the pedestrian crossing, if you want to transmit the image, actually you don't need to transmit the whole image. Only you have to transmit the pedestrian image only. So that is the part of the image only you have to transmit. So that is the semantic communication. So that means in long term, the required functions will decrease. So that by that way, energy consumption will decrease. But for short term, so until the renewable energy sources integrated with the cellular network, energy consumption will definitely increase because of the modern applications and modern more functions needed. So this is going to be this is from a technical paper. So that is when smart grid meets the energy efficient communication system. So that means then we will end up with green wireless cellular networks. So it is going to be powered by the smart grid. So that means when we have smart grid and the cellular network base station, when they are integrated, so they are going to have both, so the bidirectional communication flow as well as the energy flow. So that means these base stations, they consume 70–80% of energy of ICT sector. So they will be this energy supply will be from the renewable energy sources by integrating the cellular network with the smart grid. Okay, so now we'll come back to the question. So how the IoT devices are going to be connected? Say whether if it is smart meter or whether it is in the smart grid, we need high reliable and the very low latency devices. How they are going to be connected? So they are going to be connected using low power wide area network. So that means, so we cannot use these IoT devices connections, we cannot use the human to human communications technique, we cannot use it. So here we are going to use it, the low power wide area network we are going to use it. So why we are going to use the low power wide area network? Because so according to the requirement, the battery lifetime is going to be 10 years. So that is, if you take a smart city, so if you have so many sensors, so you cannot replace the battery of the sensor frequently. Every year you can't change it. So therefore, the energy consumption should be very low. So that's what we are going to use, the low power wide area network. So if you take the low power wide area network, so they are going to be the numerous technologies available. So some based on the ISM band like Wi-Fi, anyone can use that band. Say like, so here LoRa and Sigfox, these are the technologies to connect the IoT devices using like Wi-Fi, using ISM band, anyone can use that band. But here, if you take the cellular based one, so the fourth generation LTE based one, so here we have narrowband IoT, and this is for for high data rate. So these are the cellular based one. So the cellular based IoTs are used in the urban areas. Say for the smart meter connections, so they use the cellular based one. So this ISM band, LoRa, Sigfox, these are for the rural areas where you don't have the cellular infrastructure. Okay, so now if you take these IoT devices when they are going to be connected, so now you can see the requirements are completely different. So if you take the human to human communication, the requirements is this brown line. If you take the IoT devices connection technology, low power wide area network, so here it is going to be range is around 15 kilometer range. So if you take the smart meter, then latency is not an issue. So then it has to have the geographical coverage also high, because if you have a urban area, it has to cover the smart meters, so the several kilometers range. So now if you take the IoT devices, how they are connected, whether smart meter or the IoT devices in the smart grid, so there are two types of technologies. One is the cellular based one, this last three column. The first one is ISM band. So now if you take the last three column, so these are the one mostly used in the urban areas for the smart meter, because there are many advantages, because already cellular infrastructure already available in the urban areas, so smart meters could be connected using the cellular based IoT. So that's what, this is the evolution of cellular based IoT. So now in the 5G, this is the release 16 is the 5G standard. So now all smart meters in the urban areas are connected using this narrowband IoT devices. So that means using the existing cellular network, all smart meters are connected. Now the question is, so when we take as I mentioned earlier, for the smart grid, so the requirement is extreme very low latency. So 5 millisecond or 25 millisecond you need. So reliability is going to be 99.999%. So here we have extreme connectivity. So that is the millions of devices, whether smart meter, smart grid or smart meter, so many devices are going to be connected. So how we could achieve this connectivity is, so here in communication point of view, we have the grant based and grant free scheme. So if you take your mobile phone, to establish the connection with the base station, if your mobile phone to establish the connection with the base station, it will have to do the handshaking process. So that means say if you take smart meter, if it wants to send the data to the base station or utility service provider, smart meter will have to contact with the base station to transmit the meter reading. So that means it has to send some preamble. So then the base station will have to acknowledge and give the access to send the smart meter reading. Similarly, in the smart grid, so any IoT device or any control device to establish the connection, so they will have to do the handshaking process. That is the standard communication scheme. But if you use the normal standard handshaking process, it will take 15 milliseconds. So if you take 15 milliseconds, but as I mentioned earlier, for the high voltage, you need 5 milliseconds. High voltage transmission, you need 5 milliseconds. But if you do the handshaking process, it will take 15 milliseconds. So therefore, you cannot achieve. So that's what in the current standardization activity, they consider the different schemes. So one scheme is grant free. Grant free means, so that means the device, as and when packet arrives, immediately send it. So that means no handshaking process. But the problem is, if it send immediately, there are so many IoT devices, so therefore they will collide it. So if they collide it, so then you'll have to repeat again and again. So energy consumption also will be high. So how to solve that problem? Other one is, so that is grant free. Then how to achieve the reliability? So that means 99.9% reliability is needed in smart grid IoT applications. So if you take 99.9%, how you can achieve? Because here you have grant free. Grant free means you send immediately, you send the packet. So not handshaking process with the base station. So what will happen? They will collide. So how to achieve the 99.9% reliability is, so the symbol in the standard, they use the symbol scheme. So repeat it. Say for example, one packet is repeated, same packet is repeated 5 times. So definitely it will succeed at least one of the 5 repetition. But the problem is, if you repeat 5 times, but again the latency will increase. So at the same time, you don't have the resources you don't have. So now, so how we can achieve that one is, so in the standard, they used another scheme. So that means you don't need to wait till the last repetition. So sometimes the second repetition, the packet transmission will be successful. So therefore, with the second successful repetition, it will terminate. You don't need more repetition. So these 2 schemes, they recommended in the standard to increase the reliability to 99.99%. So now, how we are going to connect the massive devices? Because if you take the cellular operator, so the spectrum is expensive, so it is limited spectrum. So how to accommodate so thousands of devices utilize the same spectrum? So now if you take the resource block, so whether in the 4th generation LTE or 5G, if you take one resource block means 180 kilohertz is going 1 millisecond in the time domain, 180 kilohertz in the frequency domain. That is going to be the one resource block. So if you take the one resource block, so many devices can select the same resource block, then collision will occur. So how we can solve that problem? So because limited resource blocks are there, because the say limited spectrum, say for example 180, say you have 10, you divide it 10. So in the time domain 1 millisecond. So if you have the time frequency grid, so now you, for example, you have 100 resource blocks. So these 100 resource blocks are going to be accessed by thousands of devices. So therefore, how we can solve that problem? Because if you have for 1000 IoT devices, you cannot have 1000 resource blocks because the spectrum is limited, cellular based. So the operator bid the spectrum at very high cost. So therefore, you cannot have infinite spectrum you don't have. So therefore, the limited spectrum, so the limited resource block, how we can utilize. So that is, we remove the orthogonality. The remove the orthogonality means the current standard, they have orthogonality. So that means at a particular time, only one device selected one resource block. Other time slot, another device select the same resource block. But if you remove it at the same time, if two devices use the same resource block, so then what we'll have to do at the receiver, we will have to have the successive decoding scheme we must introduce. By that way, we can increase the massive number of connectivity. So these are the three schemes proposed for the massive connectivity, then 99.99 reliability, then the latency. To reduce the latency, we remove the handshaking process. So now, so the question is, so as I mentioned here, so how we are going to reduce the latency to 1 millisecond or 5 milliseconds? So we are going to remove the scheduling request, the conventional communication scheme. To increase the reliability, we are going to repeat the same packet. We are going to repeat k number of times. So to enhance the massive the connectivity, we are going to remove the orthogonality. So that means same resource block is going to be utilized by more than one user at the same time. This is the only way we can achieve the all three requirements: the massive number of devices access at the same time, achieve the reliability of 99.9% with the latency of less than 10 milliseconds. Because as I mentioned earlier, we need, for smart grid application, we need the latency of 5 milliseconds. So here, what is meant by the physical resource block? So here, so if you take the telecommunications, so this frequency is 180 kilohertz, time 1 millisecond. So here we have one signature sequence to differentiate. So that is, we call it as contention transmission unit. So that means, for example, if you take an IoT device, to establish the connection, so it has a pool of CTU. So it is going to select one CTU and send it to the base station. So that is the contention transmission unit means. So now, if you take this contention transmission unit, say, as I mentioned earlier, so here in the ground free, so we can reduce the latency. If you take the conventional scheme, say like our cellular stand, the current mobile phone, so it takes this much of time to establish the connection. So we cannot meet the requirement of 5 milliseconds. So to meet the requirement of 5 milliseconds or 20 milliseconds, so we have to remove the scheduling request, the formal grant-based schemes, we have to remove it. So by that way, we can reduce the latency to 5 milliseconds or 10 milliseconds. The other scheme I mentioned is the repetition scheme. So if you repeat the same packet a certain number of times, definitely we can improve the reliability to 99.9%. Because if you repeat the same packet 5 times, definitely at least one time it will succeed. So that is the way we can improve the reliability. So this scheme is, so once it succeeded, that it terminates. So then it does not need the repetition in the remaining packets. So as I mentioned earlier, the contention unit means, so here this is a pool of 6 contention transmission units. So IoT devices are going to select one of the CTU and send to the base station. So now, for example, you can see this CTU is idle. So that means none of the IoT devices selected from the pool. So here, if you take this one, CTU 6, so only one IoT device is selected. So therefore, that one succeed, no collision will occur. But collision will occur, say like CTU 4. If you take CTU 4, 2 IoT devices take at the same time. So now if you take these three scenarios we are going to have. So you have the CPU pool, So a particular IoT device can select only one CPU. So now we are going to have three scenarios. Some CPUs may be idle. Some CPUs are selected by only one user. Some CPUs are selected by more than one user. Now the question is, so why we need the machine learning here? So here the problem is, so here we have complex scenario we have, because whether in smart grid or smart meter, so when we have tens of thousands of IoT devices, so we don't know the channel conditions, we don't know. So we don't know how many collisions occur. We don't know how many CPUs were idle. So we don't know anything about the environment. If you don't know the environment, we cannot model the system. If you can't model the system, what we could do is, so we use the learning experience. So where we are going to use the machine learning, when we have model deficit. If you don't have the model, then we can't use the conventional optimization scheme. So that is the reason here we use the machine learning algorithm, so deep reinforcement learning, to solve this problem. To solve this problem means, so to achieve as many devices to succeed. So here we can prove that if you don't use the machine learning, say when we have 20,000 IoT devices, try to establish the connection at the base station at one time. If you don't use the machine learning dynamic optimization, only 20% succeed. Only 4,000 IoT devices will succeed. But by having machine learning, we can have 80% succeed. So that means 16,000 IoT devices will succeed. So now we are going to see the environment. So here in the environment, we are going to observe the environment means, say here all the IoT devices, say we have 10,000 IoT devices, all IoT devices are going to select their CPU from a limited pool because spectrum is expensive. So from the pool, they are going to select one of the CPU. So now the question is, observation means, so every few hundred milliseconds, so the base station will observe, okay, say for example, during the previous 500 milliseconds, how many CPUs were idle, how many CPUs collided, how many CPUs succeeded, they will observe. At the same time, how many devices or IoT devices finally successfully transmitted the data. So smart meter data or smart grid data, or whatever it is, succeeded. So these 5 observations will be done in the base station during the certain 500 milliseconds. Then in the base station, we have agent, machine learning agent. Agent means one software. So here we have 2 agents we have. So one agent is going to select the repetition value. So that means that if you repeat more time, you can improve the reliability, 99.999% you can improve. But the problem is, if you repeat more, say more than certain value, so we cannot support many devices because resources are wasted. So that's what, so the agent, machine learning agent, observe the environment and change the value dynamically. Every 500 milliseconds, the machine learning agent at the beginning of the 500 milliseconds suddenly change the repetition value. Say, for example, during the previous 500 milliseconds, more collision occur. So then at the beginning, so the agent will increase the repetition value because the channel is very bad. So during this 500 milliseconds, so all devices succeeded. So then it reduces the repetition value. Similarly, number of CPUs. So here, if you have more CPU, it is fine because collision will not occur because everyone will select a CPU to transmit. But the problem is we cannot have infinite CPU because spectrum is expensive. So CPU should be adjusted, because if you use the whole spectrum for the IoT, smart meter or smart grid, then we don't have the spectrum for human to human communication. We don't have the spectrum. So spectrum is only certain amount is allocated. So that should be efficiently used. So therefore, we have two agents at the base station. One agent every few hundred milliseconds change the repetition value. Other agent is going to change the number of CTU. So by changing every few hundred milliseconds, so they can solve this problem. So they can successfully serve more user equipments. If you don't use the agents, what will happen if it is the current standard? If you take the current standard implementation without machine learning, so what they do is they use the load estimation approach and they don't change dynamically. Say they keep it for several thousand milliseconds, they keep the constant value of repetition, constant value of CPU, they keep it. So then it will fail. Only 20% will succeed. So now if you take the scenarios we are going to have. So these are the agent structure. So we use the Q learning two agents. Now the traffic scenario we are going to see. Say if you take the general traffic, it's not a problem. Say as I said, so general traffic, so we don't have any problem. Sometimes if we have bursty traffic means so more devices try to access. So bursty traffic means so more devices try to access. So more IoT devices suddenly within this 2-3 milliseconds, so 20,000 devices want to access. Just an example. So here the last one. This pay as you drive is an example. Similar example you will get it in the smart meter or smart grid environment. Also you will get it the bursty traffic. So bursty traffic means within the few seconds you have 10,000, 20,000 devices try to establish the connection, IoT devices. But the problem is if you have 100 devices, that is no problem. So where we are going to have this bursty traffic is just one example. So pay as to drive means nowadays, so we pay the car insurance monthly fixed. But in some countries, they introduce pay only when you drive the car. Say if you park your car this month and you went on holiday, you don't need to pay the car insurance. So when you take your car to the road, so your car must be insured. So that means the sensor in your car will try to establish the connection with the insurance service provider. Insurance service provider will give the permission, okay, you can drive. Then your car is insured. Then once you park the car in the destination, so the sensor will inform, okay, now car is parked, so no need the insurance. So that means, so only 2-3 hours only you have to pay the insurance. That is pay as you drive. If you take a big football match, after the big football match, 20,000 cars leave from the stadium. So these 20,000 sensors will try to establish the connection. So that is, then they will fail. Only 4,000 will succeed. So this is the bursty traffic scenario. This similar bursty traffic scenario will occur in the grid. So that means during 2-3 seconds, within the few seconds, 10 seconds, so huge number of IoT devices will try to establish the link. So that means they fail. So if they fail, say if it is the car pay as to drive, so then you can stop the car. But in the power system, if the control fail due to the bursty traffic, then the system completely fail. So therefore, how to solve this bursty traffic scenario in the smart grid or in the energy sector? So we need the machine learning agent we need. So that's the reason of we use the machine learning agent. So this is in the standard. So this is in the standard. So the 4th generation standard and the 5th generation standard, how to model the bursty traffic. So bursty traffic, the recommended model is this alpha beta distribution. So we can model it mathematically. So here you can see bursty traffic during this few seconds. So during this 10 seconds, so huge number of devices try to access. So we can model using the parameters. We can model so high bursty traffic and low bursty traffic. We can model it. These two are high. These two are low. bursty traffic suddenly occurred. So now we use the agent. So machine learning agent, we use it for this bursty traffic scenario. So here, so 20,000 devices, 20,000 devices during that bursty traffic. So when we have this bursty traffic within 10 seconds, so we are going to divide the 10 seconds into number of few hundred milliseconds. So every second 1,000. So 10 second, 10,000 milliseconds. We are going to divide 10,000 milliseconds into few 500 milliseconds, 500 milliseconds. We are going to divide. That is the transmission interval. So now these two agents, they dynamically change. This is one agent. So one agent every few hundred milliseconds is going to change from 12 or one of these four values, discrete value agent. So other agent is going to change 1, 2, 4, 6, the repetition value. So these two agents observe the environment and dynamically every few hundred milliseconds they change such that more devices successfully establish the connection or successfully transmit the data. So in that scenario, so here we consider the scenario, the base station is at the center and the IoT devices within the 10-kilometer radius. So now we found that here, so this machine learning agent, so the red line, so dynamically changing the parameters. But if you see this solid line, so this is the current standard in the cellular standard. So if you use the current load estimation based fixed number, so here repetition value is fixed at 8. Here it is fixed, CDU number is fixed at the highest number 48. So instead of fixing the value to here, instead of fixing at the high value 8, high value 48, if you fix it, you can't solve the problem of bursty traffic because you fix the high repetition value. So many devices cannot use the spectrum. So here you allocate 48. So many devices, they don't have the CPU to take and transfer. So by dynamically changing at the beginning of every few hundred millisecond time frame, so then more devices quickly establish the connection within that few hundred milliseconds. So then we have the latency constraint. So if the device is not able to transmit within 2 milliseconds, we assume that it is failed. So when we use the machine learning agent, okay, so here it changes dynamically. So now in the standard, now in the 5G standard, to reduce the latency further, they introduced another scheme. Because if you take the 4G standard, so they have the frame of 1 millisecond, subframe of 1 millisecond. So that means in an IoT device, if a packet arrives in the middle, it will have to wait 1 millisecond. At the beginning of the subframe only they can transmit. That is in the 4th generation LTE. Now in 5G, what they did, so that 1 millisecond they divided into 8 slots. So each slot is going to be 0.125 millisecond. So now in the 5G, if a packet arrives, they can start in the beginning of any slot. So by that way, the waiting time is going to be 0.125 millisecond. So by that way, we can reduce the latency by 1 millisecond because we need every single millisecond is important. So that's what here in the 5G standard, they use the new scheme is multiple configuration grant. Multiple configuration grant means, so every device is going to select one of the configurations, whether transmit during at the end of the first slot or second slot, third slot, fourth slot. So we are going to have 8 configurations. So by having this slot 1, we can reduce the waiting time, we can reduce it. Not only we can reduce the waiting time, But also, say in the earlier, the fourth generation, if a packet arrives, it will wait till the beginning of next subframe. So two users will wait till the beginning of next subframe, then they will collide. But now in the slot-based one, as and when the packet arrives, immediately transmit. So no need to wait, then the collision can be reduced. So this is the motivation of the 5G standard in release 16. They proposed this multiple configuration grant to reduce the latency of critical applications. So now the same thing here, you can see some device can start from second slot, some can start from first slot, some can start from 0th slot, some from third slot. So every slot is going to be 0.125 milliseconds. If this one slot base is not introduced, say if a packet arrives here, it will have to wait till here. 1 millisecond it will have to wait. So now the same thing. So we are going to have one more agent. Earlier we had two agents, single configuration, we had only two agents. One agent repetition, decide the repetition, other agent decide the number of CPU. Now we have third agent. So that agent is going to decide for this user, second slot is the best. This user, third one is the best. So therefore, so we have three agents now. So now the agents, so these three agents, they are going to take three parameters: repetition value, the starting slot, number of CPU. So we are going to have so many combinations. If the agent select the correct value such that more devices will be served, reward will be given to the agent. If the agent select the wrong value, penalty is due. So that is the principle of reinforcement learning algorithm. So now here when we have one more agent, so that agent so is going to here this agent, it can slot 0, slot 1. This is the new agent. So now when we do this, say here we found that so this when we have multiple configuration grant, so the machine learning algorithm performs well. So here green and red. So here single configuration grant failed under bursty traffic. So during this time we are going to have bursty traffic. So multiple configuration grant succeed, single fail, because the reason is multiple configuration grant does not need to wait till the beginning. So 1 millisecond it saves. Here we have latency constraint we have. So within 2 milliseconds, if we don't submit, we don't succeed, we assume that it's failed. So that is the reason. So in the new standard, 5G standard, they propose the multiple configuration grant. So again, the latency. So when we have multiple configuration grant, we have the latency of less than 1 millisecond. So this is what we needed for high voltage smart grid. So now we can see when we have more configuration grant, so we can reduce the latency further. Say when we have 5 configuration grant, latency is 0.8 milliseconds. So at the same time, under the bursty traffic, the performance is also much better. The more devices successfully served. So now the conclusion is, so whether smart meter or smart grid, so now we need the 3 requirements: massive connectivity, latency should be 5 milliseconds or less than 5 milliseconds. Then reliability should be in grid, reliability should be 99.99%. Otherwise, the system fails. So reliability for every case should be. So to achieve all these 3, so what we need, in the standard we have multiple configuration grant, but in the standard the optimized value are static. But if we have the static, it won't work. So that is the purpose of machine learning in the IoT for the critical application. So now, so here if you have more configuration grant, so we can have we can reduce the latency further and we can serve more. So these are the references. So that is the end of my talk. So actually here most of you from energy background. So machine learning is utilized, say in other cases also machine learning utilized. Machine learning utilized, say all data are collected. So from smart meter, all data are collected. So to optimize the energy consumption, energy saving, all those things, to analyze the data also machine learning utilized. But since my background is in the telecommunication, I used the connectivity of the IoT devices, whether in the smart grid or whether it's in the smart meter, how to successfully connect the IoT devices to the utility service provider or to the base station using the massive IoT, critical IoT technique with machine learning. Another domain is so to collect the data to analyze using the machine learning tools, how to analyze and to save the energy. So that is another domain. So that is I have not been worked on that domain. So that domain only the energy or power system researchers only they analyze the massive data collected using machine learning tools. Okay, so any questions?
I don't know if any questions from the audience. Please.
Two questions. First, maybe I don't have a background on the one of human.
Yeah.
Said like for variability, we can for time repeat the
Yeah.
different stuff.
Anytime, yeah.
Does it mean that like only or for you like the region or is it normal protocol just so you need acknowledgement.
Yeah. So,
I don't know how.
So that to stop that one, the proactive scheme, every repetition they have acknowledgement. So succeeded or not. So, yeah. So then this one actually increase the communication load because instead of sending only one acknowledgement at the end of the last repetition, for every repetition when you send the acknowledgement or non-acknowledgement, so the communication load will increase. Yeah, the normal communication system we have acknowledgement. Yeah.
But so they use the action on the media stadium.
Actually, these agents first to be trained. For training, it takes several hours. Once it trained, so then online decision every few hundred milliseconds.
And did you consider the carbon footprint impact of adding this machine learning layer on top of the protocol?
So this machine learning algorithm, the agent's consumption of the energy. So nowadays the computing power significantly increased with the low energy consumption. So compared to the other power consumption, the computing energy consumption is not significant because now low power computational facilities are available now.
So you train your agents on a specific first
Pattern, yeah.
Do you face or do you face situation where you never face the given pattern of the first data? So it's now exactly how to do it. But you have a way to learn online or
so actually to train actually we should use the real data set, but we don't have the real data set. So data set by simulation using that model, we generated the software. Using the software, we generated the data set using that model alpha beta distribution. Yeah, so we consider the all possible alpha beta parameters.
They are, I mean, in the field, giving us the gesture, we also have, you know, I would like to show a little bit the activity here in Luxembourg in this area. I know they are weather. Maybe we can introduce the company of you as well, and we can have some discussion.
Okay. Thank you very much. So good afternoon, everyone. My name is Gregory. I'm one of the co-founders and head of operations at Data Things. It's a Luxembourgish company created 6 years ago. Our core business is doing software engineering and software engineering for data analytics, machine learning, doing artificial intelligence for various systems. And one of the core projects we have been working on since several years now was, well, and still is, a project with Creos in Luxembourg, where we actually help them to create a digital twin by learning from the smart meter data that are provided by all the smart meters deployed in Luxembourg. So it's 350,000 smart meters deployed on the territory in the Luxembourg, in the Creos realm. And those smart meters send every 15 minutes 4 values. That makes every day 134 million data points that are collected and learned from to create profiles of consumptions, load profiles for each point of distribution in Luxembourg that are metered. And from that, from the information from the grid, from the network, then we can really create a digital twin by learning. And this tool is called Alva, and is currently used in operations at Creos to help them simulate, anticipate the impacts of deployments of more electrical vehicles, the deployment of more solar panels or windmills on the grid, and see where to increase the capacity of the grid to face the energy transition. So I guess that's for a short introduction, and we can go for the questions after.
Thank you very much.
So my name is Jun Tao. I'm from LIST SES unit. So my research is focusing on the application of the artificial intelligence in the specifically on the energy system. So we are focusing on mainly 2 areas. One is using the smart meter data from Luxembourg and also public data set to do the forecasting. So we use the historical data and using this new technology we developed to predict the energy demand. And the other area is specifically for the management of the distribution grid. So because we have more and more EV and also renewable in the distribution grid, so we're using deep reinforcement to optimize and control the battery and the EV to reduce to better manage this distribution grid. So, thank you.
Okay, maybe you can take a chair. Do we have a second microphone here? Well, I don't know if you have more questions from the floor, technical questions. I mean, in my case, regarding this reliable communication, when you are talking to the retransmission of packages, no? I think this kind of technique requires, let's say, somehow, I mean, what I mean is you talk about decodes, but when decodes are moving fast, I think ensuring such a retransmission of the data sets communication, is this a challenge as well to ensure such a reliability, such a kind of communication, or not, or it's not a real serious issue for that, for ensuring such a reliability?
So the reliability issue will come. If it is general traffic, it is fine.
Yeah.
So the reliability problem will come whenever any bursty traffic scenario occurs. Bursty traffic scenario only the 80% fail. Okay. So to improve the reliability in the bursty traffic scenario only, the machine learning needed. If you don't have the bursty traffic, general traffic, you don't need machine learning. So if it is a normal traffic, so you can use the current standard load estimation based approach, method of moment matching. That's in the current standard. So it can succeed. So reliability issue comes whenever any unexpected burst scenario occurs, whether the high bursty or low bursty. So say sometimes low bursty also may occur, not necessary to be 20,000, maybe from 200 to 700 suddenly. So those kind of scenario, so if we don't have the machine learning dynamically optimizing the parameters, it will fail.
But I guess also heterogeneity could be an issue, no? To have so many heterogeneous systems with so many different state packages because the machine learning will be having work.
So here we have 3 agents, but normally if you consider several other scenarios, so we may have more than 3 agents.
Well, just going a little bit more to the question from your perspective of your experience, Gregory. We are talking about 3 milliseconds, 5 milliseconds latency.
5 milliseconds, yeah.
5 milliseconds, okay. Thinking of long bin. So what do you consider would be possible to do with 5 milliseconds latency or reality? And at what level? Because now you are developing systems which are running within the range of 1 second, no? Or well, I don't know.
So on our case, basically, and in the case of the electricity grid in Luxembourg, the data are actually collected along the day. And it's in Luxembourg, the smart meters, at least for electricity and gas, I think, are communicating with power line. So no 4G on those smart meters. The data are transmitted along the day, collected, and then put at disposal every 24 hours.
Okay.
So at the very moment, on the side of how we are using the data at the moment, we have a frequency of data every 15 minutes, but we get the data only the day after. This is the state of the status at the moment. This will most likely accelerate in the coming years, I would say. Yet for now, it allows and it enables to learn and be able to predict more flexibility already in the grid by every 15 minutes. There are new models to create already on the grid at this scale, on the 15-minute scale. New models for the distribution of energy. There are also models on cost of energy, the impact of industries, the impact of different consumers, the impact of the cars. So there are already a lot of models to create, to learn from, to try to predict and simulate. So we are not at the moment. We are really on the distribution side of the smart grid with Alva, and we are not in the piloting of the grid. Not yet. Maybe in the coming years, but we are not piloting the grid directly. When we reach this step, when we need to actually pilot the grid, most likely we have to reach those kind of few milliseconds, because otherwise you can have equipments on medium and high voltage that will suffer quite a lot. And so at the moment, the systems in place are probably handling the situation, but we anticipate that we will need more tools and more support to help face those transitions with more injections, with more use also of the energy, and then probably in the coming months or years, we will need to increase the frequency of the measures, and maybe then other technologies like the 5G, 6G, and those improvements and the help of AI will really unlock management of more of maybe smaller grades or subgrades, and yeah, this kind of things.
Okay. Well, actually, this matter of the subgrades of the, let's say, the initiation, no, the problem is something to do when we use the lighting, no, that's when,
Like,
no, it's on that, no, but it's more or less, I mean, from the perspective of communication, is on the direction, no, maybe you could elaborate a little more what the interest of the lighting when we deal with this kind of for improving or for achieving, improving reliability and improving the fast or
the network slicing. So according to the requirement, say some applications need very low data rate, some application need very high data rate, some application need latency issue. So configuration will change according to the requirement. So by the so the configuration is not fixed. So configuration will dynamically change according to the what type of application you need. Say for example, if you take autonomous vehicle, so there you need high data rate at the same time less than 1 millisecond latency, otherwise car will meet accident. Say if you take smart meter, you don't need the latency millisecond, no, you don't need the latency at all, the smart meter. So latency is not an issue, data rate is not an issue, few packets not an issue. So data rate, latency, reliability, these three for different applications. So configuration will change for according to the application.
And well, then look in this line of granularity from your perspective, June, I mean, well, the grid tomorrow is say how let's say consisting of multiple small systems, no? Small communities, small grids. What's your vision about how to manage such a grid, how to use artificial intelligence at that level to generate such a kind of fractal system consisting of several units? Could you, what is your perspective on
yes,
that?
I think in the future we will have more and more this kind of small scale like analytic community. So they are connected and they are operated. I think in the future they will more operated in autonomous way, so they can like using more and more IoT to sensoring to get real-time data. I think for in the future the smart meter data will be connected in real time, so they have more and more real-time data, and you can get this data and also analyze in real time using machine learning and AI. For example, using the deep reinforcement learning to learn from the historical data, and then you can control it in a real-time way for this small scale, so they can operate in an autonomous way. And then in the future, you will have lots of money. This huge amount of agents. They need to cooperate with each other, and then to provide a more intelligent and also more efficient way to operate. I think this is kind of we call it multi-agent deep reinforcement learning to do control and optimization.
Okay. I don't know if there is any question from the floor. I mean, regarding this advanced, let's say digital system based on communication, distributed. I mean, there was a question from the online audience regarding what kind of computational capacity, what kind of, I mean, what is the effort that is required for running the system respect to the technology that we have today? Do you consider technology at the computational level today is ready to meet the grid or the user requirements, not only in terms of technological capacity or computational capacity, but also from the perspective of price and affordability, or do you consider this necessary to make some additional? I mean, you are talking about running neural networks locally and computing information and sending, let's say, some process information to other nodes. How is our technology ready? Maybe a cell phone, yes, but what about the smart meters or the technology that we are using today in smart grids? Do you consider that it's already a challenge as well at this technology level, or do you consider technology ready?
So in terms of technology, I think for what is regarding AI, I think we have to always try to separate indeed the training of the models and the inference phase. Once a model is trained, querying the model or saying what is your prediction, what is your decision in this kind of situation, this is not really computational heavy. It's quite easy to handle, and on very small platforms it can be done. The question is more on the training of the algorithms, the training phase, and this is today we can see the developments of ChatGPTs and LLMs and etc. And those are very computational heavy because they are using a lot of data. At Data Things, we try to also work the use of hardware, cloud, thinking about where we are doing the computation, how we are doing the computation. Because if I take the example of Luxembourg, we managed to have the entire smart grid of Luxembourg over the history of almost 3 years now. So it's close to 150 billion data points to load for the entire country, and this today runs on one small server that is it's one server. Okay, it's a small investment. It's a 10,000 euro server. Okay, but we made the choice to have a physical server here on our premises with NVMEs, with taking care of the disks, making care of the RAM, taking care of the architecture of the computer to make the computation. Most of the AI training today goes to virtual machines that you can rent here and there on different providers that you can find on the market. However, you have to keep in mind that each time you use the cloud, you are also using virtualization. So it gives you virtually a lot of power, but there's also a huge amount of this power that is just used for the virtualization phase. And by also thinking where and how you are running your algorithms and how you use, for instance, your language, your libraries on Python or whichever, how those elements are used to actually develop your machine learning algorithms and train them is very important also on the to try to have clean learning too, because if the goal is clean energy, the way to go should be a clean way also. And that joins the question of Sylvain to Nala a few moments ago, on saying how much does it cost to train your algorithms. And yes, this is also one of the good questions. So I think we all have to, in this domain, AI is a powerful tool, and it's a tool we have to use, and machine learning is something we have to use, but we probably have to be also careful how we deploy this, how we use this, and in what environment we deploy and train this, because this is also important.
Yeah. Actually, this is something Sylvain was explaining in the last meeting, in the last lecture. Well, at the end of the day, artificial intelligence is getting a very relevant player in this new world, making many decisions. But well, it's something which is not already certified. Okay, there are not certifications about artificial intelligence decisions. Okay, there are certifications about efficiency, there are certifications about protections, certifications about connection, security. But what about artificial intelligence? Okay, the decisions taken by artificial intelligence are absolutely relevant, but who is that? Who is certifying that today? No. Well, this is something that Silva was raising, and that Silva was raising last time, no? And maybe Guy, I can give you a microphone and you can this is something.
You summarize well. So there is this new regulation at the European level with the AI Act, and indeed, like if we have Creos like who is buying a product from Data Things, who is using AI, so there will be, I assume, in the future some regulation and pressure from government to get certified things, but we don't have yet a certification agency that are ready to certify this kind of product. So it's more like a question mark of what will be the future in this. I don't have the answer, but I think it's part of the ongoing work also of the EU.
Maybe in the future, electrotechnic certification on the IC certifications soon.
One question to agree, because we discussed with Manti who from Germany, and they have a certification agency for the electric energy sector, but that are certified devices and so on. I don't know in Luxembourg who is doing this kind of, do you know? Or?
Maybe you can introduce yourself a little bit.
Yeah, exactly. I'm Xavier Hansen from the Ministry of Energy. I can try and get that one. Actually, there is, I mean, the Creos and other DSOs comply with the standards. They also have a lab to test the equipment and certify that it's according to the norms. However, the Luxembourg certification body ILNAS does not have any competencies on metering of that sound. This discussion that we are having now, if that is needed also in the future for with the evolution of things. I'll use the opportunity to have the microphone to ask another question, maybe. Maybe it's, I mean, my background is more in mechanical engineering and environmental policy, so I'm quite far from this subject, but does this optimization of latency have an impact on security of data transmission? Because obviously, if you're talking about piloting the grid, about getting operationally into the energy systems, that's a quite critical question. So is that dealt with on a different layer? Is this also a concern in this optimization of the latency that you have to have trade-off with security questions?
Yeah, actually, security is a most important thing, but here we mainly concentrate on the machine learning algorithm to select the suitable parameter, only 3 parameters. But we haven't considered the security. Security is the most important thing because, for example, one IoT device is hacked, then the whole system will completely collapse. So therefore, security is a most important issue. But here we haven't considered the encryption or anything, any keys or anything. We haven't considered that. Just we consider the basic data, but at the high level application layer. So the security issues must be considered.
Actually, from my perspective, no, when you were talking about the capacities of IoT today, no, and even when you're talking about this not practice, okay, this very fast communication where there will be a lot of diversity of packages, even spare packages, and the system should be really intelligent. But on the other hand, you are talking about finding seconds for us. Protection. It's not operation even, it's not planning, it's just protection. No? So it makes me to think, well, now we are deploying an infrastructure of smart meters. You mentioned we are now going for 15 minutes, maybe 5 minutes granularity of the computation. We have a technology running seconds today, ready maybe to go to the market. No? So my question is, my question to myself, I mean, maybe the technology that we are deploying today is already, it's already let's say, not ready for really or not, it's not, or it's already, I don't know, totally, or it's not already at the level of really satisfying the requirements that the system could generate, okay, because we are, the smart meter, you know, with the dongles. When I was talking before about I was talking about this NetLab, no, the dongle for 1 second, no. even 1 second is too slow for you, no? I mean, 1 second for you is an universe, no? I understand your words, no? So, I don't know, this is what I was thinking today about what would be possible, no? Because I have the feeling, of course, you said for driving, 1 millisecond is, or 5 milliseconds is necessary, no? For controlling, for automatic driving. The systems, I mean, reaction in case of alignment of a fault or any kind of oscillation is also understood. Okay, and today we are running with protection, but suddenly are disconnecting part of the system. But maybe this capacity that is, I don't know, because I mean, I don't know this what you presented now today. How much is this today what you presented research oriented or is a research or is a conceptual, let's say, over positioning or conceptual view of the system, or how much is this something that could be really applied and in the market? In this kind of solution, do you consider we will have them in the market in a few years in a close horizon?
I think so. Maybe in another 4 or 5 years.
5 years. Because in 5 years, we are deploying now all the smart metering infrastructure, the construction we are running, and which is thousand more smaller than the one you are mentioning. So maybe that problem.
I think there's also a notion of use and goal and aim, and the infrastructure that is deployed today for the smart metering is meant to digitalize the metering data for invoicing, for also seeing what's happening in the distribution network. And being able to have data, to be able to simulate from the real data and from the real consumption and drive the investments on the grid. What we are talking about here and what I can imagine for the future is when we have more injections on the territory, when you have more solar panels, wind farms, etc. And you have a cloudy day like this, and suddenly you have a big sun and then a huge injection. Then probably at some points we need also to deploy the distribution operators or the transmission operators need also to deploy security systems, additional security systems that will have to communicate in those kind of ranges to also take action on the grid to ensure the smooth distribution, to ensure the stability, to ensure or maybe to cut some gas generations because there's more solar power at the very moment and for the next 10 minutes or something. So we will probably have to reach this kind of equipments, but I think we are not today. The grid is in a state where they have this kind of equipment on the transmission and for the control of the grid. Yet the smart metering information are not yet used for live implication. So there's no closed loop from the meter data to acting on the grid. And today, as I was saying, we get the data from mixed metering 24 hours after they were collected. So it's absolutely no go for the 5 milliseconds that are required on those kind of live piloting of the grid. Yet, I think there will be some experiments also on these kind of things, also including the Smarty Plus giving more seconds data on various things. So I think there are still things to do, use case to imagine, and there's no unique one technology, and there's probably a mix of different communication technologies for different goals, I would say.
And well, I'm thinking maybe June, in your case, no, from the perspective of, because we are approaching everything from the technology itself, or the features of the technology, but from the operational perspective, the systems we are talking about, the one we want to manage, are very, let's say, heterogeneous system and plenty of uncertainty. So from your perspective, how much learning could help to decrease such uncertainty in the new energy systems, okay, and something similar? What kind of uncertainty do you consider should be faced in order to, and what are the challenges, okay? Because now we talk about thousands of communities where we should train systems just to be managed, okay? So what is your perspective about how artificial intelligence, computational intelligence should address such a heterogeneous and massive issue?
Yeah, I think this is true because in the future we will have more and more uncertainty in the especially in the distribution grid, because in the transmission we have already many monitor and sensor to control and monitor the grid, so it's reduce uncertainty a lot. But for the distribution grid now we are still facing a lot of challenge, like the smart meter mentioned. The data actually is not closed in the loop, so you receive the data one day behind. So I think the challenge is we need to have this kind of communication is very important. So we have this real-time communication to receive, and also the IoT to have the real-time data from the user and also from the grid. So this is one challenge. And the other challenge, if we have lots of this kind of data, how we utilize this data to generate new knowledge and to provide more intelligent control, optimization, and forecasting. I think forecasting in the future will be more and more important for this distribution grid, because for the transmission, the forecasting is already quite good. So I mean the accuracy, but for distribution, because it's related to the behavior of the individual household, and also we have more and more renewable in the distribution level. So forecasting is really challenging. But if we think, imagine we have combined these two, we have more and more data with this IoT, and we have the artificial intelligence like the ChatGPT. So you can train actually the foundation model for the energy field. So you have big, large foundation model for the energy field, and then this model can give you more robust and more generalization, so you can improve the forecasting. Because the reason I'm thinking like this, actually there's a debate like whether we're using a small model or big model for the industrial or for system. I think because it's this, I mean the very the results from, I mean, using this ChatGPT, I see, you know, the big model actually can give you a good or accuracy result. So I think in the future, in the energy, we will have this kind of foundation model to provide robust and accuracy forecasting. And I think this big model, because training it is very time consuming, and also you need lots of resources to support it. But it also, because once you train it, it's much easier to maintain, because currently we have lots of small models for each household, for each company. Maybe they have their own model to do the prediction, but it's not easier to maintain. In the future, if we have this large scale model, and then you can train it using different data set, and then using the transfer learning, you can use the basic model and fine tune for different tasks. I think this can save the energy and also improve the efficiency. This is my
maybe. If I may, a question from my side on this. I mean, you can feed these models with a different amount of data, right? And do you think that we have to go down to a granularity that each smart meter has to be in the loop in the future? And the background of my question is that the current lax metering meters have now, I think the first ones have been put in 5-6 years ago, so they're about half of their lifetime. So soon the the question really arises what the features of this next generation smart meters will need to be. Do you see those already as sort of real-time in the loop meters, or will that technology first have to be on transformer station at on a bit higher level to feed those grid models as a first step, and really you ever need this complexity also of having very like granular smart meters in every household, which obviously comes with a cost and comes with the complexity of data communication and things that may also have other impacts.
Yeah, I think this is a good question. I think it's quite necessary, and also we need the smart meter in the loop and in the real time. And also, I think in the future, the smart meter not only a sensor or monitoring the devices, it will be a kind of like edge computing. So they have their own computation resources. It's lightweight. It's not very heavy, but they can you can deploy some trained model, like in the cloud, you train your neural network, but you can deploy it actually in a smart meter devices. So they can use to optimize and also to give you some better control for the household. So you have this monitoring, and also you can actually give you some control and operation from these smart meter devices. It will be edge computing devices. I think this is my point.
I would like to say something in this regard. There is reading a report from members. They were talking about everything here in this room is controlled by electronics. Okay? How much expensive would be to include one of these ESP chips in whatever field? And Wi-Fi communication is sending the real consumption to the mobile. So that is the need. Okay? Here in Luxembourg, we are sensing how much we are consuming from meters that they are consuming without so the politics of the smart meter is still even today already I think we are grasping at the technological activity, and the smart meter is working late. Maybe back 10 years ago or 15 years ago because the technology was ready. And now we are implementing something. We mentioned just both single lamp. You mentioned the vehicle will be only paying insurance when driving. No? Here, okay, many of these lights will be more expensive. Why not take thank you to mobile what they are consuming? Okay, and in addition, if we are talking about simple, it would be possible to have I know. I mean, we're speculating here in the university forum over here. This is what we should do, okay? So, actually, maybe my question is in this regard. So, I don't know for you, how nice, because here we are talking about this kind of futuristic things, no? But at the end of the day, the end users, which are outside of this room, they are quite skeptical sometimes about artificial intelligence, about, I mean, probably they would be dependent on that. But so how do you consider the governments, nations, or institutions should promote this? Because since it's unstoppable, not the use of all these technologies for managing the new system that could not be represented by a model. So, by a model from the perspective of formulated, no? So, what do you consider? Well, first of all, Gregory, you had another point, but your point on that, and the second one is, please, what do you consider? What kind of measures could be taken in order to accelerate this integration, this expansion, this penetration of this technology?
The first part of was a continuation of the answer. I think the smart meters deployed today still have a bit of action that can be taken to offload a bit some elements. There's one port that you can connect something on to offload things. And today, I think the aim is to ensure the stability of the grid and to face, for instance, the increase of the electrical vehicles, because those are and electrical pumps. And the physical grid will have some physical limits, and in the coming months, years, in some places in Luxembourg, we might reach those limits, and we have already to find some good mechanism, policies, strategies to be able to share, and I mean share the infrastructure and the energy on one street, for instance, or one cable. That means that the charging of your electrical vehicle might not be 100% the full night. It might be few sections of the night that you will be allowed to load, because you have to share until the grid is upgraded. Okay, and this comes maybe also to the second part of the question. There's already at this point, at this level, a lot of questions on who's deciding what, who makes the decision, and it comes also maybe from on those ideas for certification. There will be somewhat an artificial intelligence, an algorithm, something, a planning that will decide you on this part of the street, you will not be able to charge your electrical vehicle or use your heat pump for a certain period of the day, like 2 hours this night between this date and this date. Is this acceptable? Is this not? If we even think further and say, okay, here we are talking about the smart meter that is able to offload one specific device in your house, should there be able also to offload part of your appliances in your house? I guess it's my personal point of view. This is only about me. I think there are two different things. There's one where the distribution operator have to ensure the distribution, the stable distribution of energy, that everyone in the country have electricity 100% of the time and with quality. And this might imply already to offload part of your personal requests and personal loads. And this already asks a lot of questions. And then there's probably more a private part. If you want to install something in your house that will give more information about the consumption of your different devices, the technology is already there. You can already have the consumption of your different devices on your smartphones. You can load, offload, you can start, stop things with programs. You can learn also your own habits and have a program and AI driving your house for that. But I don't think it's the role of the government or any public entity to also go further from the smart meter into your house. They have to stop at the smart meter because that's where the electricity distribution mandate stops. And already with this offloading to ensure the distribution, we are getting a little step inside, and that asks already a lot of questions. So yes, AI, there will be questions on how reliable this is, but I think also in the domain of energy, there's a lot of watchdogs and security mechanisms. There will be also, as we said, physical, mechanical security mechanisms that will ensure the proper distribution, even if the algorithm at one point sends an order that is completely out of physical laws. There will be the physical laws to remind the artificial intelligence that this cannot happen. Okay. So I think there are ways to reassure that artificial intelligence and machine learning are tools that we can use when the human brain or the Excel spreadsheet cannot comprehend anymore the complexity of the system. And we know what are the inputs, we know what are the outputs, but we don't know how it works. And that's where machine learning can help with reinforcement. And I think this is clearly one of the very good use cases. And people, public, will get to know how it works, will get with time to know and get and trust those technologies. But it's not because we entrust the technology that we cannot control also what it does. Trust does not remove control. And I think we have, and that's what we say also to our clients, if you plug it on the real system, make sure that you ensure that the outputs remain in the bounds that are okay for your running system, because we cannot also guarantee what the system, what the output will be 100% of the time. It's machine learning. So yeah.
And maybe, you know, like we are already close to time. Sure, you preparing many proposals for government institutions and technology. That proposal, sometimes you have to start to explain by the impact. So, what do you consider could be the impact of this new technology, new artificial intelligence, and revolution at the level of using massive IoT? Or you have the case of energy. But from the economic perspective, what do you consider could be the impact? I mean, not only for energy, what do you consider could be the most, let's say, relevant impact of this new
Say, if you take the economic impact, so this massive IoT economic impact, say, by observing the smart meter reading and analyzing the data, so we will be able to say we can see the pattern, the usage pattern we can learn. We learn the pattern using this artificial intelligence or machine learning. So we will be economic impact. Will be able to save the money. So that means they automatically for the users we can say dynamically we can say. So today, say due to some other function, so this time, normally this time maybe usage may be low rate, but today this one may be very high rate. So the machine learning algorithm, so by giving the prediction, so that will be able to save the money of the consumers.
And from such a perspective, okay, we talk a lot today about user-centric systems, okay? Do you consider this technology could really empower users at the central part of the system? Because communication was one of the tools used by the centralized system, by the transmission operators and so on, and this is why the transmission system was working well with the cadency of the second, let's say, at the time. No? But now these new technologies, do you consider could move, let's say, the system top down and really to make the end user to be empowered in order to play a different role in the energy system, thanks to this communication, this capacity for interacting with the system, with the markets, with the other interoperability with other sectors and so on?
So you mean the machine learning artificial intelligence in power system?
And IoT as well, yes.
Massive IoT.
Because I think, let me just explain myself a little bit. Okay, we talk about blockchain as a kind of, not exactly, I mean, a layer technology that is proposed with enable end users for doing many things that so far was not able to. As soon as you increase the capacity for communication.
Okay. Or one example I take. Say, for example, nowadays, say, I don't know here the situation. So in UK, to find a car parking slot, we will have to sometimes we will have to drive 4-5 miles. We will have to drive here and there. Anywhere we cannot find a nearby parking slot. We cannot find it.
Yeah.
So if you have the massive IoT, the sensors in all parking slots, that if that one is integrated, your what's that? Economical, which one is this one? So all these combination, it can directly your sat-nav go to that path. So by that way, you can save a huge amount of fuel or huge amount of electrical energy. Because to find the car parking, so maybe 20 minutes you drive here. For 20 minutes driving, how much fuel is cost? How much, if it is electrical vehicle, how much energy cost? So this one could be saved if all car parking slots with the IoT devices connected to the internet. So then your sat nav, you set the setting. So that means within this place, within 1 kilometer radius, the cost should be 1 hour, should be less than 1 hour, less than £2. This constraint you select, then your sat nav, this is the optimal place because it shows that where the free slots are there. We don't know now where the free car park slots are there. So sometimes we park at a very expensive car park. So all these, if you take all these car parking slots with the sensors, it's connected to the internet. So you can save the energy, fuel or electric vehicle.
I think you, Gregory, could give us example how this capacity for interoperability communicating at the energy system level for improving optimization, reliability, stronger control of your PV generation, when you charge the vehicle, when you charge the battery.
I don't know if it's more a question of it is at one point a question of communication, okay? Because we could also imagine that the cars themselves could ask a central system when is the most appropriate time slot to load, for instance, depending on the load of the grid or the planned load on the grid. I think it's also maybe more than communication means, it's also intercommunication and APIs and machine to machine to set in place. Because indeed, one can make a decision saying, okay, this part of this street we will stop the electrical vehicles for 2 hours because otherwise the cable will just melt. And then 2 hours later it would be this part and this part. But maybe just maybe, there's this person living here actually don't charge at night because they work at night, and then maybe we can charge during the day and keep whatever, these kind of things. The parking, the same thing. If we know parking slot, the question is more, how do we interconnect those systems? How are they able to communicate together? How are we able to also aggregate, for instance, weather forecasts, so that we can have a smarter way, a smarter planning from the learning, aggregating all the information that makes sense and that impact, for instance, the distribution or the life or the traffic on the road, and have everything connected and have a kind of smart guide to help us go somewhere, find a parking spot. And the backbone behind this is surely communication. And for some appliances, low latency is surely a must. For some others, it can be a little slower because we have in our domains also some appliances on trees. For trees, days are enough, okay, in terms of communication. So yeah, I guess it's also it's communication, but it's also how we can connect smartly elements and different systems to make things even smarter, probably.
Thank you. I don't know if you have any writing methods to conclude our presentation from your perspective, I mean, about the evolution, your vision, what do you consider we go to from your area?
Okay, so
you
now
should encourage people to say, okay, guys, like you are the new generation that is interested in you work on this, on that, from your perspective.
Okay, so now artificial intelligence, machine learning in almost every field, whether you take robotics, whether you take industry automation, or wherever it is, the artificial intelligence and machine learning is an important topic nowadays. Say one simple example is the technology available is SLAM, simultaneous localization and mapping. So when I was in the Heathrow airport, I saw one robot is cleaning the airport. So it is cleaning the airport. So if it does not have this SLAM, simultaneous localization and the mapping technique, so what it will do is it will clean the same place again and again. It won't go to the other places. So to go to the other places, so this artificial intelligence machine learning approach, so it gives, so from the sensors, it collect the where the objects they are, here this object, that object, all these data and everything, and the machine learning trained algorithm, it guides to go to the different places and clean the different places. If it is not, then it will clean the same place again and again. So that's one example. So similar to many other examples. So that's the reason. So this artificial intelligence, machine learning, in almost not only energy sector, communication sector, or industry automation sector, in many areas. Now, just for an example, if you take the MSc degree program, artificial intelligence program, the class MSc student 200, just normal MSc in communication only 20 students. So the 200 students, they go there because of job opportunities and marketing, all those things. Because even in economics also, so the prediction, everything, so they use the machine learning within the economics.
Thank you very much. Well, thank you all for your time. Now we are going to take a coffee and we will be able to our presenters today, and thank you really very much all of them. Thank you. ¿Eh? Sí, ahí fuera. Sí. Now you have your